The universe is a beautiful place. As astronomers, we observe the skies and take glorious images of stars, galaxies, and other celestial objects. As stargazers, we marvel at the sights in the night sky.
But should we really be so trusting of our eyes? Are we too dependent on the narrow band of visible light that we happen to be able to see?
Over recent decades, we've expanded our ability to probe the universe using the whole spectrum, including invisible light, from X-rays to radio waves.
Our ability to see beyond the visible has dramatically changed our understanding of the universe, allowing us to investigate things which we simply cannot see. In this programme, we're looking at the ways we choose to represent the universe.
We'll be asking whether our ears might not tell us just as much, if not more, than our eyes. Meeting some remarkable people who have learnt to use their other senses to probe the mysteries of the universe.
Just because you can see something, does that mean you're getting the full picture?
And just because you can't see something, does that make it any less real?
So whether you're watching or listening or a combination of both,
welcome to the Sky at Night.
When I tell people I'm an astronomer, I think they imagine that I spend my nights on some distant, lonely mountain top staring through the eyepiece of a giant telescope. But it's not like that at all. Most of my colleagues have never looked through an eyepiece, and we spend our lives staring at screens. But in return, we get to go beyond the limitations of our eyes and see the cosmos in new ways.
The colours of the rainbow are actually different wavelengths of light. Red having the longest wavelength and violet the shortest, in what we call the visible spectrum. But of course the electromagnetic spectrum extends much further, with wavelengths of light that are invisible to our eyes. Going from short wavelengths to long, gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves and radio waves.
I'm here at 𝐁𝐞𝐲𝐨 Bank, Britain's celebrated observatory dedicated to radio astronomy. Director of the observatory is Tim O'Brien. Well, Tim, thanks for having us. It's always good to be in the shadow of the Lovell telescope. But I guess my question is, why does it look like this? It's not what people expect from a telescope.
No, I mean, of course it's a radio telescope, so it's not picking up visible light, it's picking up radio waves from outer space. For thousands of years, obviously humans have looked at the skies with their eyes. When the telescope was invented 400 years ago, we got a better view, but we were still confined to that bit of the spectrum. The radio telescopes let us pick up a completely different set of information from space, so we see completely different things. I think if you could imagine for a moment, if we had radio dishes for eyes, and we were looking up now, one good thing is we'd see right through these clouds. So it's a completely different view. It revolutionises really what you understand about the universe.
And it helps us explore the universe beyond what we can see with our eyes. As well as the Lovell, 𝐁𝐞𝐲𝐨 Bank is home to a number of smaller radio telescopes, including one dedicated to studying one of the most famous objects in the sky, whatever the weather.
Now that's a great telescope. That's called the 42-foot telescope. It spends virtually all its life pointed towards the Crab Nebula, as it's doing exactly now. So just above Orion over there.
We are here in the rain. This is a sort of typical Manchester day, and there you are observing happily.
Yep.
The Crab Nebula is the remnant of a supernova that shone briefly in the sky nearly 1,000 years ago.
When we look in that direction now, we see this sort of glowing, expanding patch of gas.
But of course, how it looks depends on what telescope you use and what wavelength you look at it with.
Indeed, yeah. I mean, this is actually a picture of the Crab Nebula made with a radio telescope. That's false colour. The colours are representing the brightness of the radio waves. What you're seeing here is radio waves being produced by relativistic electrons. So electrons travelling at almost the speed of light, and they're spiralling around the magnetic field inside this expanding nebula. As we move to the to shorter wavelengths, we come to the infrared. And again, here we still see some of this hazy blue stuff there from this population of relativistic electrons, but also now we see emission coming from the dust grains that used to be part of the star. Now moving to shorter wavelengths, we see the most famous picture of the Crab Nebula now. This is in the visible light with the Hubble Space Telescope.
Okay, but we can keep going. We don't have to stop at the visible.
No, we can keep going. We can go to shorter wavelengths. We head out of the visible, and here we're into the ultraviolet. Then you're going back towards just this hazy stuff again, but it's also sort of contracting.
Yeah, this looks like you've cut out the centre of the nebula here.
Yeah, and that actually gets even more pronounced when you go to even shorter wavelengths and you go to the X-ray. So
Wow.
This is quite remarkable, really. These are all to the same scale on the sky. So now you're only seeing the very central parts. And in fact, you're sort of starting to see this sort of very bright spot right in the middle, surrounded by what looks like a disc of material.
Sort of a donut
Yeah.
around the centre. And then are those jets coming out?
Yeah, in
from
fact,
it?
there's a nice little movie of this.
Oh, wow.
It's particles, it's matter and antimatter accelerated to almost the speed of light. This is the pulsar. So this is a visible light picture. You see how this thing is flashing. Basically, you see a bright flash, a faint, a bright, a faint. That bright flash is happening 30 times a second. We now know that these things are neutron stars, so it's the central core of the star that exploded, that collapsed in on itself. It made this dense object about the size of a city, about 20 kilometres across, spinning round, and it shoots out beams of radiation from its magnetic poles.
You're a radio astronomer, I'm an optical astronomer, but actually more and more we're learning that you have to put all of these things together to understand what we're seeing.
The frustrating thing about being an astronomer, we're never going to go and visit these things that we're interested in studying. So what you do is you gather as much information as you can across the whole electromagnetic spectrum. Each of those bits of information, I like to think of it, it's like a piece of a jigsaw. So you've got your X-ray piece of the jigsaw, your radio piece of the jigsaw, your visible light piece. And it's only when you put all those pieces together, you get this complete picture of the object you're interested in.
But even pictures taken with visible light may not show exactly what we'd see with the naked eye. This image shows my favourite object, the Orion Nebula. I love the complexity and the detail that you can see in this stellar nursery. But were I to fly past it in a starship, this isn't what I'd see at all. Instruments like the Hubble Space Telescope are much better at picking out fine detail than my eyes could ever be. And the colours in this image were chosen to convey specific information.
Hubble has produced some of the most incredible colour images of the universe ever taken. But the amazing thing is, it doesn't even have a colour camera, just a black and white one. To create a natural colour image, Hubble uses filters to take 3 black and white images at wavelengths broadly corresponding to red, green and blue. Back on Earth, these images are given their colour and then combined to make a full colour image. It's a natural representation, even if the original pictures are in black and white. It's actually how our eyes work too, with different cells picking up red, green and blue light, and then the brain creating an interpretation of all the other colours. Other images are made using what is called the false colour or narrow band technique. This is where the camera takes 3 black and white pictures using only very specific wavelengths of light, emitted by particular elements like oxygen, sulfur and hydrogen. These pictures are then assigned the primary colour, red, green or blue, closest to the original wavelength, and a composite colour picture is created. Images made like this allow astronomers to represent the ingredients of a galaxy or nebula, to show the composition of the gases. It's a visual way of representing the data, but it's not what Chris would see when he's flying past in his spaceship.
Shame. How we perceive colour is ultimately dependent on context and subject to interpretation. And for scientists, the particular colour palette doesn't necessarily matter. What they're after is the information, the data hidden in the image. If they have to use fake colours to extract it, so be it.
If you want to explore colours in space, you can always have a look for yourself.
Well, what do you know? It looks like it's going to be a clear night. Certainly waited long enough for one. That's really exciting. Ooh, I hope it works. Well, you probably think that with all the furore over Venus last month, that the planet I would be trying to look at would be Venus. But as far as amateurs go, the planet of the month, the planet of the next few months indeed, will be Mars. And the reason for that is that Mars reaches opposition in the middle of October. That means that the apparent size of Mars is close to its maximum. In fact, it's up there at the moment next to a bright moon shining away at me. Okay, so here I am with an image of Mars, which is fantastic. And what I've got there is a view of Mars which shows its characteristic colour. It's sort of orangey, salmon pink colour, I always call it. It's probably not quite right, actually. It's probably more ruddy than that. It's quite a beautiful colour. And it's due to the fact that Mars is rusty. It's got a lot of iron oxide up there. The image is gradually getting worse, and that's because the front of the telescope is dewing up. There's lots of moisture in the air drifting through now. I must say I'm struggling a bit, wobbling all over the place tonight, but it is possible to see some detail. There's the bright southern polar cap, which is really small at the moment because it's the southern hemisphere summer. But the most striking feature is the dark exposed band of rock which I can see running almost equatorially, slightly south of the equator. Because the atmosphere is wobbling things, I'm grabbing thousands of frames over a short period of time. And what I'm going to do is pass those through a special program which is going to filter out the best frames. Well worth staying up. Very late. Well, good morning. It's a beautiful day. The sun is shining, and I had some fantastic captures of Mars last night. So all that remains now is for me to process them to see what I got. Now, in these video files, there are images of Mars, still frames of Mars, some of which will be really distorted by the atmosphere, some of which will be really crisp. And the process now is to try and get the crisp ones out of the movie file. And that's no mean feat, because sometimes the movie files can contain thousands of images. But fortunately, there are some bits of software, and I'm going to run an analysis on it. Now that basically looks through all of those frames and it decides which ones are the crispest. It's basically taking all those good, steady images and combining them to give me a much better result than I could reasonably expect if I had taken just a still image. Now I'm going to put that into a sharpening process. Oh yeah, you can start to see the detail coming out quite nicely there. So if you have a clear sky and you go outside and you can see that bright orange glowing object up there, then that is the planet Mars. Get outside, have a look at it, and good luck.
Astronomy has always inherently been a visual science, but not everyone is able to make use of sight, and we have other senses that can be used to explore the mysteries of the universe. Well, Nick, thanks for talking to us. I'm intrigued by the objects in front of me, but we'll get to those in a second. Astronomer Nick Bond from Portsmouth University is going to guide me into the realm of the tactile universe. For me, I grew up thinking of astronomy as a visual science. I was a kid that looked at the night sky. How did you come to find your way into astronomy?
So I think when I grew up in the early 80s, the Voyager probes had just started to send back images of the outer planets in the solar system, all those beautiful shots of Jupiter and its moons, Saturn, Uranus, Neptune. And given that I've got a tiny bit of vision, I was able to sort of put my head right up against the screen and get a sense of the kinds of colours and the shapes and everything else like that. It got my brain going. I started thinking about how far away those planets were from us, but then how much further away everything else in the universe was. And I guess from that moment I was hooked on astronomy.
But then as a professional astronomer, how have you been able to work with data in your professional life?
So that visual side of things was always a little bit complicated. In terms of making plots and other things like that, I actually developed my own sort of style of doing things. I worked with galaxies during my PhD research, and luckily we can represent most of the characteristics of a galaxy using numbers. So even the shape of a galaxy can be represented by a sort of string of numbers.
Now, as a professional astronomer, Nick has developed a set of 3D printed galaxies based on real data.
So I guess I wanted to make things a little bit easier for anyone who is vision impaired and young or old and wants to learn more about astronomy. I wanted to sort of create some really, really useful resources that people could just grab and use to learn as much or as little as they want to about objects like galaxies. So that's what we've got in front of me. I think that I've got a set of galaxies here. I'm going to pick one randomly. How do I use this? With most of these galaxies, we've centered the galaxy in the very center of the tactile model. So what I would recommend doing is starting off in the very middle and probably use your pointer finger. Okay. So what you want to do now, you can either sweep from side to side or you can start spiraling outwards with that finger and sort of see what you can start to pick up. It's interesting because I suddenly realized I have to do something systematic here. I was sort of just expecting to be able to just almost pick it up. I can feel there's a bulge at the center, there's something large at the center, and then it seems to drop off pretty quickly. I think this may be a spiral galaxy. And then there are some pointy bits maybe at the end. Maybe would those be representations of clusters, or would those be artifacts? They could be foreground stars, they might be background galaxies. Yeah. Whatever's in the image, because the lovely thing about this is real data from real telescopes. So it's got all the junk that we expect to see in the background or in the foreground. Right, because this is data, that's the point. It's not some sort of stylized galaxy. Because a galaxy will appear different if you use a red filter rather than a blue one, Nick prints different models of each galaxy based on different wavelengths of light, each one giving different information about the galaxy. In some ways, I think using these tactile models, we can get a little bit more information if we sort of just focus on the blue, just focus on the red. In an image, I can see that with blue and red, but I can really feel the difference there. That really gets across how the different wavelengths tell you different things about the galaxy. I'm going to swap to a different one. M86 is an elliptical galaxy, and it feels, well, it's essentially just a smooth blob. It is, and it's funny, obviously when we look at that image, we see that with our eyes as well. It has a very smooth profile. The thing I love about this particular one is when we look at an elliptical galaxy, our eyes kind of trick us into seeing something that's a football or a rugby ball shape. So we see this very round sort of structure. Yeah. Whereas in reality, these galaxies don't really have a definite edge. The density of the stars that make them up get less and less and less until we hit a point where the density is exactly the same as the space around these things. So they don't have a hard edge like our eyes kind of make us think. No, and moving my finger from the center towards the edge, I don't think I can tell you where the galaxy ends. That's it, exactly. It just kind of merges with the background. You definitely experience these galaxies differently by feeling them. What reaction do you get when you show this to the public? Generally, we get a really positive reaction. With the vision impaired public, people are excited that we've made something with them in mind. They're feeling something that people have talked to them about, but they've never really experienced before. When it comes to fully sighted people interacting with these models, I think, as you've discovered as well, it's just a really exciting and different way of accessing something that you might be a little bit more familiar with. And you will get different information out of it, and that's a good thing, because I think the more ways we can get to data, whether we listen to things, whether we look, whether we touch, it's always going to give us a slightly different experience, and it's always going to be a valuable experience for that reason.
Like many astronomers who have the benefit of sight, I rely heavily on visual representations like images, plots and tables to do my research. But ever ready to learn new skills, I'm about to get a lesson in listening.
Lucy,
Hey.
sorry. Lucy, okay. Good morning.
Good morning, Wanda.
Hi, how are you doing?
I'm doing very well, thank you. How are you?
Very good. So let's do it.
Wanda Diaz-Merced is an astronomer who lost her sight early in her career, but who has remained determined to continue her exploration of the universe by turning data into sound.
People think of astronomy as being a highly visual subject, but actually it's all about data, isn't it?
Yes.
Could you tell me about the sonification process? How do you turn a data set into sound?
The telescopes, what they monitor is different intensities of things happening in outer space. What we found is that it is possible to use a very basic technology to translate those measurements into sound equivalents. Every single measurement has an equivalent in tones, in volume, or amplitude.
How did you come across the sonification technique? What was it that triggered an interest in using that in the first place?
I was losing my sight very fast. And at that time I was lost. I was like, I'm in the physics department. I cannot do the experiments. I cannot, I was trying to find a way to perform in the science with no options.
But Wanda's world took a new course when she heard her first fragment of data turned into sound.
When I heard the data the very first time, real time, that opened a world of possibilities for me. I think I have the same right you have to participate, to mainstream in the scientific field. When I was supposed to be doing my PhD, I found that I couldn't do it, that I didn't have access to the same amount and quality of information, not even the tools to be able to do the science. That thrilling sensation, that independence, right, of me being able to manipulate the data real time, to dynamically apply mathematical states to the data, that had been completely taken away from me. And what sonification does is that it brings me back. I get too excited.
I think it's brilliant, and you have a right to be excited, and you have a right to access these data sets.
The problem that we have right now is that now we have to compete with the visual development. And when we propose to use sound, it's never taken as a possibility to do science.
Could you give me an example, Wanda, of a data set that you sonified, and tell me a bit about the research that you did with it?
Okay, so this is the GRB. Okay, so I think I have it.
Great.
This is the sound of data collected by the SWIFT satellite of a gamma ray burst, among the most energetic explosions in the universe.
It's a gamma ray burst that happened as a result of a supernovae explosion.
It's very regular, which I don't know if I should expect that or not, actually.
You're not listening to the explosion, to the big explosion. So we are listening a little bit before the big explosion happens.
Ah, it's before.
We cannot see them, right? They are very energetic. The gamma ray bursts are very energetic, but humans cannot see it. And we can only see an itty-bitty tiny portion of the electromagnetic spectra. So regularly people translate it to the visual, and I was able to translate it into sound.
By turning the data into sound, Wanda was able to uncover information about gamma ray bursts that would otherwise have been beyond her reach. And she identified outflows of stellar material that had hitherto been hidden.
Outflows from the exploding star may be associated with this gamma ray burst. We are listening to indications of that outflow. An interesting thing is that we were able to identify outflows are indicative of a spreading of a material that is needed for the birth of new stars.
And do you think you get different information from the data if you're listening to it versus if you're looking at it?
When people use sound as an adjunct to visual display, their sensitivity increases. So there's a lot of information that your eyes are missing.
What research do you plan to do in the future using this technique?
Right now, I'm involved with a project at the European Gravitational Observatory for citizen scientists to study gravitational waves as a door to bring a sonification to the study of gravitational waves. In the case of my hopes for the future, the only thing that I ask is to allow me to mainstream. That is my biggest hope, for people not only see us as people with disabilities doing science like something on exhibit, but as human beings that have other ways to perform science equally or better.
I have to admit, I found it hard to pick out those subtle patterns in Wanda's data, but then I haven't developed the same precision in listening as she has. I do think, though, that turning data into sound can have a really important role to play in astronomy. It means Wanda and others like her who don't have access to visual data can be part of mainstream science. And if it opens up a new way to explore the universe, I'm all for it.
Ultimately, data is just data. And if we can open up our senses beyond the visible, then many more discoveries can be made.
After all, to really tackle the universe's mysteries, we need every tool, every wavelength, and every sense we've got.
Good night.
With guests including Sir David Attenborough, Liz Bonin explores the impact of climate change on our world. What planet are we on BBC Sounds. Next, France 1915 and Women Run the Farm. Stunning French cinema, The Guardians.